So, what on earth is a second stage analysis? A second stage analysis is effectively, it's also known as contrast testing. And if your overall or your omnibus ANOVA model is significant, then you have to go on to do contrast testing, or you have to go on to second stage analyses. And these are specific kinds of analyses that tease out where that significant difference lies. So again, they are sometimes called second stage analyses as they follow the overall ANOVA. They're the second part to the ANOVA. Technicality with this. If you have a planned design, if you have hypotheses, if it's a priori, whatever term you want to use, technically you can skip the omnibus and you can go straight to second stage analyses. And the reason for this is, if you were commissioned to be on a study and you're given a hypothesis, having a non-significant overall technically doesn't answer the hypothesis question. You still need to test the hypothesis explicitly, even though the odds are it's going to give you the same result. So what this means is, if you do have a hypothesis, you are perfectly justified in skipping the overall. However, you are also still justified in running it. You're more than welcome to, but it is a little bit redundant in that you run the ANOVA, it's non-significant, you still have to test that hypothesis anyway. So it's up to you what you do. So, contrast testing. The whole idea of contrast testing is that it can compare the means of your groups from your ANOVA without inflating your type 1 error rate. So it's kind of like a t-test. In fact, you do get t-statistics when you do this through Stata. But the way that we define our significance and the way that we obtain a p-value changes. The catch is, there is absolutely no real convention as to how you should change this p-value. There's many different ways that we can do this, and each way has pros and cons. So there's 3 different ways that we're going to talk about. We can use what's called a Sheffe, a Bonferroni, or a Tukey's adjustment. And each of these 3 approaches to adjusting significance, to controlling for type 1 error, comes with its own philosophy. The general philosophy across all 3 is that we are punishing ourselves for multiple comparisons. So the fact that we are looking at different levels of a 1 IV over and over and over again means that we could be inflating our type 1 error rate, inflating the chances that we will find a significant effect when one doesn't exist. So we punish ourselves for this by making it harder to find significance, by reducing our definition of sufficiently unlikely, by reducing our p-value cutoff. Now, this punishment of our definition of significance is going to change depending on the philosophical approach that we take, or depending on the adjustment that we make. So let's look at Sheffe. Sheffe used to be very popular once upon a time, but you don't see it too often anymore. What Sheffe says is, once you've looked at your means, the second you've run your descriptors table and you see the means of your groups, you have already made decisions about what may or may not be significant. You have already run every single test in your head. You haven't done it formally, you haven't calculated T's and F's and p-values and significance, but you've looked at them and you've gone, oh, well, you know, that's group 1 is 10 and group 2 is 20. They might be different, but group 3, that's 11. 11's not that different to 10. So you're making these comparisons in your head. So Sheffe would argue that once you've looked at your means, you've already run every comparison you should, therefore you should be punished effectively for every possible comparison. This is the philosophy that goes most nicely with a post hoc design. So in a post hoc design, you are, in one way or another, going to test every possible comparison you can. And so, because Sheffe has the philosophy of punishing you for that approach, Sheffe is the most appropriate test. So this is where really knowing whether or not your design is planned or post hoc is absolutely crucial. Because if it's a post hoc design, you're probably going to run a Sheffe. You're going to use Sheffe in your contrast testing to adjust significance. Bonferroni is another kind of correction. It's extremely common, mainly because it's really, really simple. Bonferroni holds the philosophy that you should only be punished for the comparisons you want to look at. So whereas Sheffe is going to adjust our definition of significantly unlikely, it's going to adjust our cutoff for significance based off every possible comparison we could make, Bonferroni says, well, let's literally adjust our 0.05 for just the number of comparisons that we do want to make. So if we only want to make 3 comparisons, we take our 0.05, we divide it by 3, and we give each comparison its own chunk of 0.05, so that when you add it up, they all get it's a total of 0.05. Now this maps perfectly onto the philosophy of a planned design or an a priori design, where you've used theory to specify hypotheses. You haven't looked at the means. You haven't made conclusions based off the means, because if you did, then technically you're in the realm of Sheffe. If you've made your hypotheses and your decisions about what to compare prior to collecting your data, then you've got a planned design, and Bonferroni is perfectly acceptable. Now, just to muddy the waters, let's talk about Tukey's. So Tukey's basically goes, well, Bonferroni takes the number of comparisons and just blanketly divides that by 0.05. Sheffe looks at every single possible comparison, but what neither of these actually take into account is the amount of error in the model. So Tukey's can take into account the amount of error as well as the number of groups. So it's sort of like Sheffe but with an extra feature added to it. It doesn't care about how many comparisons you will make. You're going to get a single value that's going to represent the smallest difference that is significant. And then you can run as many comparisons as you like. So it's very much like Sheffe in that it is a sort of every single possible comparison is being considered, but it's in the context of the amount of error in the model. Now, this strongly relies on variance, and particularly relies on the fact that there is equal variance. And the thing that's going to affect equal variance the most is sample size. So what you want for Tukey's is a balanced sample. So what this means is you want all of your groups to have the same n, because as n starts to change, so does your standard deviations, even if your mean doesn't change. So Tukey's is most appropriate over Sheffe when you have a balanced design. So that's a lot of information, so let's just take a moment to think about what all this means. The first thing I want to talk about is, in terms of what all this means, is power. And power is your likelihood of finding something significant. So what that means is if I ran these 3 tests on the same 2 sets of means, on the same contrast, the most powerful would produce the smallest p-value, the least powerful will produce the largest. Even though the means and the standard deviations and everything else is the same, each of these tests will produce a different p-value. Now the most powerful, generally speaking, will be Tukey's. And what this means is that Tukey's will produce the smallest p-values. Bonferroni is in the middle, and Sheffe is the hardest to find significance. It's for this reason, Sheffe being the least powerful, that you will almost never see it used in the real world. However, there's a technicality. There's always a technicality, right? A note on power. Tukey's is more powerful than Bonferroni, but this is only true when you're looking at all possible comparisons. So if you've got 3 groups and you're looking at the 3 different comparisons that you can make, Tukey's is probably better. But if you're only interested in one contrast, then the odds are Bonferroni will actually be better, because Bonferroni will then give 0.05 for that entire contrast, whereas Tukey's is still going to account for all possible contrasts. So it's just a technicality that this ranking of power only applies if all contrasts are being considered. If you're only comparing some of the contrasts, then Bonferroni is probably more powerful than Tukey's. Generally speaking, if you're only looking at a select number of comparisons anyway, you're probably in the realm of a planned design, and Bonferroni is the way to go. So, I have a lovely table here that tries to summarize all that information. If you have a planned design, you're doing Bonferroni. That's just the blanket approach. Bonferroni adjustment if it's a planned design. If it's a post hoc design and it's balanced, you use Tukey's. If it's unbalanced, you use Sheffe.